In the last few lectures, we have examined momentum balance in a pipe flow due to a pressure gradient. The pressure is something that is different for momentum transfer in comparison to mass and heat transfer. Mass and heat transfer mechanisms are convection and diffusion. Momentum transfer, there is convection and diffusion, of course. Newton's law for viscosity applies for diffusion. However, there is another mechanism which is a pressure difference. Pressure is a force per unit area acting perpendicular to a surface. It acts along the inward unit normal to the surface. What we are dealing with here is the dynamical pressure, okay, that is the pressure difference in pressure between the local pressure and a reference pressure. Okay. And flow is driven by a difference in pressure between two locations or by variations in pressure, not whereas the thermodynamic pressure is an absolute pressure, okay, whereas the dynamical pressure is a pressure relative to a reference pressure. And for an incompressible flow where the density is a constant, it is only the variations in pressure that generate flow, not the absolute value of the pressure itself. So, we had gone through the calculation for the momentum in the axial direction in a pipe, and this was the equation that we had got. Okay. For an incompressible flow, okay, this was the equation. The left side is the inertial terms, the variation of Vx with respect to t. On the right side, the first term is the viscous term and the second term is the pressure gradient. Okay. We had also shown by mass balance that Vx is independent of x, okay, that Vx is independent of x for an incompressible flow if the density is a constant. Okay. So, if the density is a constant, the velocity Vx is independent of x. And by taking the derivative of the momentum conservation equation with respect to the x direction, we had shown that d square p by dx square, this has to be equal to 0. Okay. The variation of pressure with respect to r has to be 0, and the second derivative of the variation of pressure with respect to x has to be equal to 0. Okay. That means that the pressure gradient dp by dx is only a function of is a constant, okay, or the pressure is a linear function of x. It is a straight line between the pressure at the inlet and the pressure at the outlet. For an unsteady flow, the pressure at the inlet and the pressure at the outlet could vary with time. However, at each instant of time, the pressure anywhere within the pipe is a straight line, is on a straight line between the pressure at the inlet and the pressure at the outlet. We had derived the velocity profile for the flow in a pipe. Okay, we had derived the velocity profile for the flow in a pipe by using the momentum balance equation with a constant pressure gradient for a steady flow. Okay, by using the momentum balance equation with a constant pressure gradient for a steady flow. This momentum balance equation, the pressure gradient is a constant, so we could solve it, and for the velocity profile we got a parabolic profile which is called the Hagen-Poiseuille flow, okay, with the maximum at the center at the axis and 0 velocity at the walls. The maximum velocity we had shown was equal to 2 times the average velocity. Okay. By doing an integration over the cross section, we showed that V average is equal to 1/2 of V max, or V max is equal to 2 times V average. Okay. And V max was related to the pressure gradient. Okay. So, V max was related to the pressure gradient by this expression. Note that minus dP by dx is positive. V max is positive if the pressure gradient is negative or the pressure at the inlet is higher than the pressure at the outlet. And finally, from the relation between the wall shear stress and V max, we got an expression for the friction factor. Okay, we got an expression for the friction factor as a function of Reynolds number. This is the friction factor that we had used earlier for a laminar flow. Okay. For a turbulent flow, this does not apply. As you recall, we had discussed when we did dimensional analysis, the friction factor for a turbulent flow. You can get it either from the Moody charts, okay, or from the Colebrook relation or other approximate relations. You can get the friction factor for a turbulent flow. In general, the friction factor for a turbulent flow will be higher than that for a laminar flow. And I should also note that this friction factor is the fanning friction factor. Okay. The Darcy friction factor Fd is equal to 4 times the fanning friction factor, and the correlation for that will be 64 by Re, okay, for the Darcy friction factor. Okay. So, let us solve some examples. Okay. The first one I will take is for the flow in a pipe between two tanks. Okay. Okay, you have a pipe with a valve in between two tanks, okay, which could add tanks A and B with height of water HA in the left tank and HB on the right tank, and areas AA and AB. Okay. So, let me give the specific numbers in this case. Okay. Tanks A and B with area AA is equal to 1 meter square and AB is equal to 2 meters square. Okay. Connected by pipe of diameter D is equal to 1 centimeter and length L is equal to 5 meters, okay, fitted with valve. Fluid of density rho is equal to 10 power 3 and viscosity density is kg per meter cubed. Is filled in tank A up to height of HA naught is equal to 3 meters. The valve is open at T is equal to 0. Okay. And we are asked to determine how the heights change with respect to time. Okay. So, when you open the valve, initially only tank A is filled in up to a height of 3 meters. Okay. And once you open the valve, there will be fluid flowing from tank A to tank B. And what we would like to know is how the height decreases in tank A and increases in tank B, and how it reaches a final steady state. Okay. The total volume of fluid at any instant in time has to be equal to the initial volume of fluid. Okay. So, that means that AA times HA plus AB times HB, okay, the total volume. If we neglect the volume in the pipe as negligible, okay, then the total volume has to be fixed. Okay. This has to be equal to the initial height in tank A times the area of tank A. Okay. So, therefore, I can get a relation between the heights of tank A and tank B, okay, just from this volume conservation condition. Okay. So, HB is equal to AA into HA naught minus HA by AB. Okay. Area of tank A is 1 meter square and area of tank B is 2 meters square. Okay. So, this just becomes equal to 1 into 3 minus HB by 2 in meters. Okay. It should be HA, I am sorry. So, this is the relation between the two heights. Okay. Now, what is the relation between in order to find out what is the flow rate, we have to relate the flow rate to the pressure difference between the two tanks. Okay. The pressure at the bottom of tank A, PA, is equal to rho g HA, okay, and PB is equal to rho g HB. Okay. Which implies that PA minus PB is equal to rho g into HA minus HB. Okay. So, that is the difference in pressure that is driving the flow. Okay. Therefore, PA minus PB is equal to into HA minus HB, which was 3 meters minus HA by 2. Okay. And I can write this as 3 rho g into HA minus 1 by 2. Okay. Because HA minus HA by 2 will give me 3 by 2 HA. Okay. 3 by 2 HA, and I have 3 by 2 here. So, this just becomes 3 rho g HA minus 1 meter by 2. Okay. Note that the area of the tank A is 1 meter square, volume the height, initial height is 1 meter. Okay. So, therefore, the initial height is 3 meters. Okay. So, therefore, there is 3 meter cubed. Okay. The sum of the cross sectional areas of A and B is 3 meter square. So, the final height has to be 1 meter. Pressure difference will be 0 when the height in both of these tanks is equal to 1 meter. Okay. Okay, when the height is equal to 1 meter, HA is equal to 1 meter, HB is also equal to 1 meter, 3 meter minus 1 divided by 2. Okay, so that is when the heights will be both different. Okay. Now, pressure difference has to be related to the flow rate. Okay. If flow is laminar, okay, we have to come back and examine this assumption after we have calculated what is the flow rate, okay, and the velocity. Okay. If the flow is laminar, then the difference in pressure, okay, PA minus PB by L, okay, which is the pressure gradient, okay, which is the pressure gradient, okay, that can be related directly to the volumetric flow rate, okay, by the relationship, okay, 8 mu by pi r power 4 into the volumetric flow rate, okay, where r is the radius of the tank. Okay. This, you recall, we calculated what was the volumetric flow rate, okay, before we calculated the average velocity. Okay. So, the volumetric flow rate was equal to this, okay, pi V max r square by 2, okay, pi V max r square by 2 was the volumetric flow rate, and V max was given by, okay, minus r square by 4 mu dp by dx. Okay. V max was given by r square by 4 mu dp by dx. Okay. Therefore, this, if written in terms of V max, so the flow rate written in terms of the pressure gradient would be equal to pi r square by 2. Okay, so let me write it somewhere else. Okay, into V max, which is okay. So, this is equal to minus pi r power 4 by 8 mu, okay, dp by dx. Minus pi r power 4 by 8 mu dp by dx. Okay. And dp by dx is minus of the inlet, it's minus dp by dx is inlet minus outlet. Okay. So, if inlet is at A and outlet is at B, minus dp by dx is Pa minus Pb by L, and that is equal to, okay, pi r power 4 by 8 mu into dp by dx. So, therefore, I get this expression, okay, 8 mu by pi r power 4. Now, the volumetric flow rate, in this case the flow rate from tank A to tank B, okay, is related to the change in height of tank A. Okay. V dot is equal to minus A A dH A by dt. Okay. V dot is equal to minus AA dHA by dt. Okay. Because as if V dot is positive, that is, there is flow from tank A to tank B, then the height of tank A decreases with time. Okay. If there is flow from tank A to tank B, the height of A decreases with respect to time. Okay. So, therefore, V dot is positive when dHA by dt is negative. Therefore, dHA by dt is equal to minus, okay, I substitute the expression for V dot, okay, pi r power 4 by 8 mu into Pa minus Pb by L into 1 over AA. and the difference in pressure I can substitute in terms of the heights, okay, minus pi r power 4 by 8 mu, okay, L into AA. Then I have in the numerator rho g into HA minus HB. And I have an expression for HA minus HB. Okay. So, this is equal to minus pi r power 4 rho g by 8 mu L AA into HA minus HB is equal to 3 HA minus 1 meter, okay, by 2. Okay. Minus 3 pi r power 4 rho g by 16 mu L AA. Into HA minus 1 meter. Okay. And I can rewrite this as minus of HA divided by characteristic time, okay, where this characteristic time is equal to okay. I can substitute the values, okay, 16 into viscosity was 10 power minus 2 kg per meter per second, approximately 10 times that of water. Okay. Area of tank A was 1 meter square. Okay. Length of pipe was 5 meters. Okay. Divided by 3 pi. Pipe diameter was 1 centimeter. Okay. The pipe diameter was 1 centimeter, which means that the radius is half a centimeter. Okay. That is 0.5 into 10 power minus 2 meters whole to the 4th power. Okay. Into rho is 10 power 3 kg per meter cubed, and gravitational acceleration is 10 meters square. Meters per second square. Okay. And you can easily see that in the end you will get just a time dimension. Kilogram will cancel out, numerator and denominator. Meters will also cancel out. Numerator you have meter square dimension, denominator also you have meter square dimension. So, you get just time. Okay. And this is equal to 1.36 into 10 power 4 seconds. Okay. Okay, so that is the characteristic time. Okay. So, d HA by dt is equal to minus of HA minus 1 by Tc, okay. dHA by HA minus 1 is equal to minus dt by Tc. The natural logarithm of HA minus 1 is equal to minus T by Tc, which means that HA minus 1 is equal to I should put the okay. plus a constant of integration, okay, which means that HA minus 1 meter is equal to some constant e power minus t by Tc. Okay. At t is equal to 0, HA is equal to HA naught, the initial height, that was 3 meters. Okay. So, therefore, this implies that at t is equal to 0, d is equal to HA naught minus 1 meter. Therefore, HA minus 1 meter by HA naught minus 1 meter is equal to e power minus t by Tc. So, this gives you the variation of the height with respect to time. Okay. This gives you the variation of height with respect to time. Now that we have the height with respect to time, we can also get the flow rate with respect to time. Okay. V dot is equal to minus AA dHA by dt, okay, is equal to minus AA into HA naught minus 1 by, okay, Tc e power minus t by Tc. Okay. So, that gives me the volumetric flow rate. Okay. The volumetric flow rate is of course largest at time t is equal to 0. Okay. The volumetric flow rate is of course largest at time t is equal to 0. Okay. At t is equal to 0, V dot is equal to minus AA into HA naught minus 1 by Tc. Okay. The area of the tank, okay, the area of the tank, if you recall, was equal to minus 2 meters into HA naught minus 1. Initial height was 3 meters and the area of the tank was, my apologies, minus 1 meter square into HA naught minus 1 meter. Okay. Should be careful here, put the units. Okay. HA naught was 3 meters, so this is 2 meters, okay, divided by Tc, which was 1.36 into 10 power 4 seconds. Okay. And if you calculate this, you will get approximately 1.47 into 10 power minus 4 meter cube per second. Okay. That is a volumetric flow rate that is going from tank A to tank B. Why am I calculating this? Okay. Recall, we had made an assumption that the flow is laminar. Okay. If the flow is not laminar, then the correlation that we had used, okay, the assumption that the flow is laminar, that is no longer valid. So, after we calculate the flow rate, we have to verify that the maximum velocity is still in the laminar regime. Okay. If the maximum velocity is not in the laminar regime, then the calculation that we have done for the flow rate is not correct. We have to go back, substitute a turbulent estimate for the velocity and recalculate the problem. Okay. So, therefore, we have to verify that the maximum Reynolds number is less than about 2100, so that the flow is laminar. Maximum flow rate is at time t is equal to 0 when the height in tank A is 3 meters and the height in tank B is 0. That is the maximum flow rate, and therefore, that divided by the cross sectional area of the pipe will be the maximum velocity. Okay. So, the maximum velocity V max is equal to V dot at t is equal to 0 at initial time divided by pi r square, the cross sectional area. Okay. which is 1.47 into 10 power minus 4 meter cubed per second divided by pi into radius is a half a centimeter, 0.5 the whole square. Okay. And the maximum Reynolds number is equal to rho V average d by mu, okay, which is equal to rho into V max by 2. V average is half the maximum velocity into 2r by mu. Okay. Okay, should be careful here. This is actually the average velocity. Okay. V dot by pi r square is the average velocity at t is equal to 0. Okay. That is the maximum of the average velocity at the initial time. Okay. So, okay. The volumetric flow rate divided by pi r square is the average velocity, and it has the maximum value at t is equal to 0. Okay. So, this is going to be equal to ten power 3 kg per meter cubed into the pipe diameter is 10 power minus 2 meters. Okay. 1 centimeter was the pipe diameter. Okay. Divided by 10 power minus 2 kg per meter per second into this V average at t equal to 0. Okay. The whole square. And if you do this calculation, you get a value of 1875. Okay. So, the maximum Reynolds number is 1875, which is less than 2100, which means that we are in the laminar regime. And therefore, the assumption of the relation between the flow rate and the pressure gradient, which we had assumed for a laminar flow, that one is correct. Okay. And therefore, this implies that we get the correct expression for the Reynolds number. Okay. So, this is an example of how the relation for a laminar flow in a pipe between the velocity, the flow rate and the pressure difference can be used to calculate the variation of the height in tanks with respect to time. In this case as well, we reduce the net effect to a time constant, okay, an exponential relation of the height with respect to time with a particular time constant. That time constant depended upon the flow properties, the density, the viscosity, the pipe diameter, as well as the acceleration due to gravity which was driving the flow due to the difference in height between the two tanks. So, this is one application of flow in a of laminar flow in a pipe. I will look at another application which is for a power law fluid in the next lecture. I will continue this then.